William.
Hi, Mr. Cowan. How are you?
Good. I don't hear any static today.
Yeah, doesn't seem like it.
Just didn't wait long enough, or did you do something different on your end?
No, nothing different.
Okay. Well, let's go like this until it becomes a problem, and if it does, I'll call you and we'll use the phone.
Okay, great.
Okay. So you got a session today and tomorrow. You must have your final on like Monday or Tuesday?
Tuesday, yeah.
Tuesday, okay. As long as we're talking about it, are you going to need a session on Monday? I got quite a bit of openings if you need one.
I'm not sure.
Okay.
If I do over the weekend, I'll probably schedule one.
You can always do it at the last minute. You only need like an hour notice to make these appointments. So
Okay.
there's plenty of time there. Sunday, not quite so much, but you could make it on Sunday also, Sunday evening or morning, if you like.
Okay.
All right, so let's see. What are we dealing with tonight? Did you send me anything, or are you going to verbalize it all?
I just verbalized it all.
Okay. This is an interesting problem. I just finished with a student. There's the function, find its end behavior and graph it. It was t to the 5th power. This looks a lot like problems you've given me also. But anyway, what do you got tonight?
The first one is let f of x equal x minus 1 all over x plus 3.
You want vertical asymptotes? You want horizontal asymptotes? You want domain?
The inverse.
Oh, that's it?
The inverse and domain and range.
Okay. So, how do you get inverses?
You switch the y and the x's.
Right. So let's first write this as y.
Right.
Okay. Switch the y's, switch the variables, and then solve for y is the way I think of it. Okay. So if I switch the variables, I have x equals y minus 1 over y minus 3, plus 3, right?
Yes.
Now solve that for y. This is a little tricky, but not that tricky. What's the first step for solving that for y? What would it be?
Multiply by y plus 3.
Okay, so I got x times y plus 3 equals y minus 1. Now what?
I'm not sure.
Yeah, well, let's distribute this. xy plus 3x equals y minus 1. Now at this point, what you want to do is, since you're trying to solve for y, you want to put everything with y in it, every term that has a y in it, put on one side of the equation, everything else on the other. Okay, so I'm going to bring this y to the left. So now I got xy minus y, and I'm going to take that 3x and move it to the right, making it negative 3x minus 1. Now can you figure out how to solve for y?
Can you divide by x?
No? The secret is factoring the y out from the left side. Notice that if I factor the y out as a greatest common factor, I'm left with x minus 1.
Right.
Now I can divide both sides by x minus 1. And that gives me y equals that. And this would be the inverse function. It's not quite right to call it y because it's not the same y as I started with. The y I started with was f of x. Okay?
Right.
So what I really have here is f inverse of x. So let's replace this y with f inverse of x. Now it's proper. In other words, I don't really want to call it y because that would indicate the y's were the same y's, and they're not. So the inverse function is this here. Now, can I simplify that a little bit? I could turn it into 1 minus 3x over 1 minus x. It's a little bit simpler. I don't know if that's a necessary simplification or not. This is something you might not know. Let me point this out. What is this equal to? Negative 1. Same thing as if I said, what is x minus 3 over 3 minus x? That's also negative 1. In other words, a minus b is always equal to the negative of b minus a. And that's how you get the negative 1s. And that's what I did when I simplified your answer here.
Okay.
The first thing I did was factor out a negative from the top. So that gave me a negative times 3x plus 1. And switch the bottom, make it 1 minus x, and put a negative in front of that. Now the negatives cancel. I wrote this wrong. It's not 1 minus 3x, it's 3x plus 1 over 1 minus x. That is a little nicer solution.
Right.
3x plus 1, it doesn't have it. It's got 2 less minus signs in it. And so it's kind of worth doing, I suppose. But
Okay.
I don't think you'd lose points if you gave that as the answer.
I hope not.
I don't think she would take anything off. Because you're not really simplifying it by turning it into this. You're just eliminating negative signs. It's not like I'm reducing any of the numbers. All right, what else you got? I can give you a hard inverse one.
All right.
How would I do this? Switch the variables and solve for y, right?
Right.
So it becomes x equals natural log of y. Now how do you solve for y?
E to the x equals y.
Yeah, well, e to the x equals e to the natural log of y. In other words, I can always, this is kind of a tricky thing. You're not taught this very often, is that if I have an equation, I can exponentiate that so that these are the exponents of any base I want. I could say 17 to the x equals 17 to the natural log of y, if I wanted to. I'm going to say e because e allows me to reduce the right side of that thing to y. So that becomes y equals e to the x, and that is the inverse of that. And again, this y is not the same as this y. This is y inverse.
Okay.
Okay? So some of these can be tough, and if you have a quadratic, they can be really tough. In other words, some inverse problems can be really hard. I don't know if you have any on your list or not, but and you have to solve them using very strange mathematics that you wouldn't think. You have to treat x like a constant for some of them. In other words, if I gave you something like this, okay, Well, now when you switch the variables, you get this. How do you solve that for y? You don't. Not easily. Notice how I could solve it for y. If I treat x as a constant and bring it over to the other side, now I got y squared minus 2y minus 5 plus x. Now I can apply the quadratic formula to that, and it's all equal to 0. So I could actually solve for y by using the quadratic formula, but this is c. That 5 plus x would represent c.
-1 times the quantity of 5 plus x?
Yeah, notice that first of all, when I move the x over, it becomes minus x, but when I put parentheses around it, it becomes plus x again. In other words, what I have circled, the two things I have circled are the same.
Right.
I have not changed the function at all. So when you have a quadratic that you're trying to find an inverse of, it's tricky. It's very tricky. And then you have to apply the quadratic formula to that. And A would be 1, B would be minus 2, and C would be minus 5 minus x.
Right.
That's what C would be. So treating x like it's a constant is the only way to do this. And it's very, very tricky. All right, what else do you have?
F of x equals 2x cubed plus x squared plus 2x minus 12.
And they want you to find the z.
Find one real zero of the function, then use synthetic division to find the two non-real complex zeros.
Okay. How do we find one? Is this a calculator question or not?
No calculation.
Okay. So you've been taught the rational factor theorem.
Maybe.
P over Q?
No.
Here's what in other words, this is not, when you get above quadratics, you know, everything up to quadratics is easy because you can always use the quadratic formula. But when you get to cubics, you can't use the quadratic formula, and there is no cubic formula. Solving cubics without a calculator is a long problem. In fact, it's liable to take us 15 minutes. Let me go through it. What the rational factor theorem says is that if there is a rational factor that is a 0, its numerator, p, will be a factor of the constant, and its denominator, q, will be a factor of the coefficient of the highest degree term. Okay? So here are my various possible numerators. Plus or minus 12, plus or minus 1, right?
Right.
It's factors of 12. Also, plus or minus 6, plus or minus 2. They're always plus or minus, no matter whether that's minus 12 or plus 12. And I got two more, plus or minus 4, plus or minus 3. So those are all of the possible numerators of a rational 0. The possible q's are factors of this 2, which are plus or minus 2 and plus or minus 1. Now, what we do is we take all combinations. Well, by that I mean we got that possibility, we got this possibility, we got this possibility, and what we end up with is plus or minus 12 is certainly one of them. All the numerators are still possibilities, but we also, so let me write all of those out. Again, But we've got some additional ones now because that denominator. In other words, we can have 1/2. We can have, 4 halves is the same as 2, but we can have 3 halves. So we picked up a 1/2 and a 3 halves. See how I got all of those?
Yes.
Okay. That's 1, 2, 3, 4, 5, 6, 7, 8 times 2. There are 16 possibles. Guess how we figure out which one is it? Random trial and error using synthetic division.
Oh.
Yeah, that's why I said it's like a 20-minute problem. So what I generally do is, since there's going to be a lot of math, I start with the simple numbers, plus or minus 1. And if that doesn't, the other theorem that is at play here is the zero remainder theorem. So here's what I'm going to do. I'm going to see if 1 is a 0. Certainly in my list of possibles. And the moment I find a 0 remainder, I will have found my 1, 0. Okay?
Mm-hmm.
And what will be left over will be a quadratic. And that's what will show below the line. Whatever 3 numbers are here besides the 0 remainder, that's what's left. And we know how to handle quadratics. We can use the quadratic formula to get those 2 zeros. So all I need to do is find 1 0, and the rest of the problem becomes easy. It's finding that 0 that's tough. Well, let me just do one of them to show you what I'm talking about. Do you know how to do synthetic division?
Yes.
Okay, let me do it for you then, just to speed things up. That does not produce a 0. It produces a minus 7 remainder. Therefore, 1 is not a 0. Let's try minus 1. Believe it or not, this is the way it has to be done. I'm not going to do all 16 of them. I'm going to graph it and see where the 0 is, and then I'll know which one to pick.
Right.
That also is not a 0. So rather than spend a half hour trying all of these, let me pull up Wolfram Alpha, graph it. In fact, I might have it up already. Hold on, I think I do. Yeah, I do have it up. What's this function again? Can you read it?
F of x equals 2x to the third plus x squared plus 2x minus 12.
Now, I know you're not really allowed to use a calculator to do this, but if you were, this shows us where that 0 is. Right there. At 1.5, which was on my list, remember?
Yes.
Plus 3 halves. That's a possibility. Well, if plus 3 halves is the 0, then if I synthetically divide this by plus 3 halves, I'm going to get a 0 remainder. Well, let's see if I do. What does that tell me? That tells me here's one linear factor. What's the remaining quadratic?
2x squared plus 4x plus 8.
And I could actually take a 2 out of that.
Right.
And then apply the quadratic formula. That becomes 2 and 4. That's not going to factor nicely. And in fact, we can tell by the graph that the other two zeros have to be imaginary. Notice that that graph only goes through the x-axis once. What that means is we have one rational factor and we have two imaginary ones. And if I look at this function, I could tell that that has only imaginary solutions, but it wants you to find them, right?
Yes.
Okay. So let's use the quadratic on this part only to find those solutions. So what's x equal? If x squared plus 2x plus 4 is equal to 0, which we can say, then how do I solve for x? What's the quadratic formula?
Negative b plus or minus square root of b minus 4ac
B squared minus 4ac
over 2a.
Right. You want to memorize that.
Yeah.
You're going to need to know that for a lot of things, but particularly for your class. That's not going to be one they give you, I'm quite certain. Okay, so now let's apply, fill in for A, B, and C. What do we get?
B is 2.
What's
So,
minus B?
Negative 2. Plus or minus the square root of 2 squared minus 4 times 1 times 4 all over 2 times 4.
All over 2 times 1.
Oh, sorry, 2a.
Okay, and now let's simplify that because they wanted imaginary answers, right?
Yes.
Okay, so I got x equals minus 2 plus or minus 4 minus 16 is minus 12. All over 2. What is the square root of minus 12 going to simplify to? The way to do these is to always take out the negative 1 first.
Okay.
Like that. Then you don't have to worry about how the I comes in because the square root of negative 1 is I. But
right.
The square root of 12, I can simplify that. That's square root of 4 times square root of 3, so that's 2 root 3. So this is actually 2 root 3 times I. So let's write that in for here. 2 root 3 times I. Now I can divide top and bottom by 2. So my final answer is minus 1 plus or minus root 3 I. Okay? Now what? Let's go up. Let me make some room here. First of all, that 2 that I took out, I can put it back in, multiply this, and it'll actually make it look a little nicer. It'll be 2x minus 3 as our factor. And that gets rid of that and that. Now, the rest of it is, if this is the zeros, then the factor is x minus that, right? So
right.
x minus, and I'll put it in parentheses, minus 1 plus root 3I. And the third factor, which I would write horizontally, but I don't have room, so I'll write it down here, is x minus the other solution, which is minus 1 minus root 3I. So those three factors, if you multiplied them together, would give you your original cubic function. That took us 15 minutes, and I used the graph to help.
Right.
Notice how long I'd still be working on it if I didn't have a peek at that graph and knew that 1.5 was one of my zeros. In other words, I would have done 1, and then I would have done 2, and then 3, and then 4, and then 6, and then probably 12, and then I would have turned to the fractions. I would have probably done the 3 halves last.
Yeah.
So 20 minutes later, I would have found my zero. And believe it or not, that's the only way to do it without a calculator. Finding the zeros of Cubix is a monster of a problem. People think the quadratic formula is hard because they have a hard time memorizing it, but it's a piece of cake compared to finding zeros for Cubix or Cortex. And the same rational factor theorem applies to Cortex.
The P and Q?
Yep. So you come up with all your possible zeros, and then you just, by trial and error, start trying each one using synthetic division. And then the moment you produce a zero, you have your other factor. If we would have started with a quartic, then the first time this is going to be a cubic, and then we have to do the same process all over again to get it down to a quadratic. So you basically take your higher degree polynomials, you use this process to find the zeros until you get nothing but linear factors and quadratics. And in point of fact, they usually, when you get to this stage here, where I'm pointing, over here, on the left in the middle, you don't generally take that down to imaginary numbers. In other words, that's called an irreducible quadratic because it has only complex solutions. And if you're factoring a cubic, you don't generally take it down to the last step like they ask you to do. In other words, my answer would be this. I would multiply that 2. My final answer is going to be that. Because I can tell by looking at this that that's an irreducible quadratic. In other words, typically in math, you go down to this step here, not down to the step they ask you to go down to.
Right.
It doesn't serve a lot of purposes. I guess it does, because if you really wanted to test it, you could multiply these all back together again, these 3 factors here, and you would produce your original cubic polynomial.
Right.
That's how hard these problems are. Now, there is one other type of cubic that does not involve having to do this. And that's if you can group it. But that's pretty rare. In other words, very, very few cubics are going to allow you to group them. In order to group it, you need the ratio of that coefficient to that coefficient to be the same as the ratio of that coefficient to that coefficient. And in this case, they're not even close. That's 2 to 1, and this is 2 over minus 12. But if they were the same fractions, then I could group it, and I can do the problem in 2 minutes instead of 20. So you always want to look for that as your first possibility. Whenever they give you a cubic and they start saying find the zeros, check and see if these ratios are the same. In other words, they have to be exactly the same. In other words, let me make that a 1. They are not the same. This one's plus 2, that's minus 2.
Right.
But if I make that a minus, now they are the same. In other words, if this was my problem, I can solve it in 2 minutes by grouping. I would group those together, factor out a greatest common factor. I think you and I have done some grouping ones, haven't we?
Yeah, I'm pretty sure.
Okay. Well, there's lots of mistakes that can be made doing grouping also, but you're beyond grouping at this point. If they're giving you cubics like this, then the only way to do these is either look up one solution in your calculator or use this rational factor theorem, which is P over Q.
Right.
And you can imagine if that's a 12 and this were a 12. Imagine your top is this numerator and your bottom is that numerator, and you have to take all combinations. So you might have 30 possible solutions. And you would just have to try them one at a time.
Okay.
Okay? So let's move on. What next?
Write a third-degree polynomial with real coefficients that has -2 and 2 plus 1, or 2 plus I as zeros.
Okay? If 2 plus I, they only gave us 2 zeros, right?
Mm-hmm.
How many are there?
3.
Right. Imaginary solutions always come in pairs. You never have a single one. So if 2 plus I is a 0, then 2 minus I is also a 0. Or I should say a solution. Because I'm not sure it's even fair to call it a 0 because imaginary zeros don't cross the x-axis, so they're not really zeros. But they are a solution to the problem. So the way I'm going to come up with my polynomial, here's my 3 factors. X plus 2, right? That takes care of that factor, times x minus 2 plus I times x minus 2 minus I. Multiply those 3 together and you have your cubic. Which 2 would I multiply together first?
The imaginary.
Yeah, because we know that's going to be a quadratic. In other words, when I multiply these 2 together, I'm going to eliminate the I, and I will have just a regular quadratic. Okay, you know how to multiply a trinomial by a trinomial?
Yeah.
Okay.
Yes.
So I'll do it real quick. That is going to be x squared minus 2x minus xi. And then I take this term, that's minus 2x plus 4 plus 2i. And I take the third term, and I got plus xi rather, minus 2i minus I squared. Now, if I simplify, you'll notice that every term with I disappears. I got a minus xi there, plus xi there. I got a plus 2i there and a minus 2i there. And the I squared turns into a negative 1. I squared is always negative 1, so this whole thing turns into a plus 1. Now, here's the quadratic that I get. That's what the product of those 2 factors equals. Now I have to multiply it by the linear factor. I'll do this real quick. If you know how to multiply trinomials, then a binomial by a trinomial, I know you know how to do that. And the middle terms usually need combining. There will only be one cubic term and there will only be one number. But I've got a total of minus 2x squareds. Excuse me, this is an x cubed there. So that takes care of that, that, and that. Then I got a total of minus 3x plus 10. There's your polynomial. Now,
Right.
first read the problem, it just said find a polynomial, right?
Yes.
Sometimes these will say find a polynomial whose constant is 20 or whose y-intercept is 20. Well, how would I get that?
Put 10 on the other side.
No.
No.
All I'm going to do is multiply the entire polynomial by 2. Remember what this is. This is equal to 0, right? In other words,
Right.
I can find the zeros, which means it's equal to 0. I did find the zeros. Well, if I multiply both sides of the equation by 2, it stays equal to 0, only what I'm left with is 2x cubed minus 4x squared minus 6x plus 20. That's also equal to 0, but these are different functions. That might be f of x. This is actually 2 times f of x.
Right.
But it satisfies their condition is that this function has a y-intercept of 20.
Okay.
It still has the same 3 zeros as the other function. And how is that possible? Well, let me draw something for you here. If I have zeros right there and right there, let's say that my function looks like this. Hold on, I didn't draw it right. I want a cubic. Okay. So there's a cubic. My black line is a cubic that has those 2 zeros where the x's are. Well, if I multiply this function by 2, it's got the same zeros. It's just a vertical stretch, right?
Right.
Well, I didn't draw it right, but here, let me give it one more shot. Let's see. It's going to go up twice as high. It's going to go through a higher y-intercept. It's going to, well, there's another 0 that I forgot about, but this actually has 3 zeros. Okay.
Right.
Both functions, the black and the red, both go through all 3 zeros, but they're different functions. They're different polynomials. The red is 2 times the black, and it's think of your transformations. It's a vertical stretch factor by a factor of 2, but it also accomplishes giving me that y-intercept of 20 instead of 10. Another way they might couch a question like this would be, they give you the zeros and they say come up with a polynomial that has a leading coefficient of 3. Well, there's our polynomial we came up with at the top of the page. If I want a leading coefficient of 3, I'm just going to multiply every term by 3, and then I'll have 3, 6, 9, and 30. And this will be the polynomial that has those same three zeros, but it has a leading coefficient of 3 now. And I would expect you to get problems like that. In other words, the one you gave me was actually the simple version of the harder one, where they give you two zeros, one of them is imaginary, so that allows you to know all three zeros. You just have to multiply those three together to get a polynomial that has those three zeros. Well, here is a polynomial that has those three zeros. But I can multiply both sides by any number I want, so there's all kinds of polynomials that would have those same three zeros.
Right.
And it all depends on that last condition that they tell you. They'll either tell you the y-intercept has to be 20 or 30, or they'll tell you the leading coefficient has to be 2 or 3 or 4, and then you take the polynomial you came up with and you multiply it in order to accomplish what they've asked you for. I hope I didn't confuse you by that, the red and the black there.
No, that
I'm just afraid that they're going to give you a question like that and you wouldn't know what to do with that condition.
Right.
All right, what else do you got?
Let f of x equal x squared minus 4 all over x squared minus 9. Find the vertical and horizontal asymptotes and intercepts.
Okay.
Graph.
Whenever you see anything like this that obviously can be factored, factor it.
Okay.
How's the top factor?
X plus 2 times x minus 2.
The bottom?
X plus 3, x minus 3.
Now, vertical asymptotes. Where?
X equals plus or minus 3.
Good. What else did they want?
Horizontal asymptotes.
Okay. Horizontal asymptotes come from the highest degree only. I don't care about the minus 4 or the minus 9 or anything else. I could have a minus 100x and I wouldn't care about it. The only thing I care about is the highest degree in top and bottom. If the exponent is equal, then the horizontal asymptote is the ratio of those coefficients, which in this case is 1. So y equals 1 is the horizontal asymptote for this function.
Okay.
Okay. If this was a 2 and that was a 3, well then y equals 2/3 would be the horizontal asymptote.
Okay.
Okay.
If they're the same degree?
Only if they're the same degree. There's basically three situations. Maybe now is a good time to cover them. There's this situation where the degree is the same. That's really easy. It's just the ratio of the coefficients. There's this situation where the bottom degree is bigger. Doesn't matter whether it's 3 or 4, okay? That always has a horizontal asymptote of y equals 0. As long as the bottom is bigger than the top, it's always y equals 0. And the third situation is where the top is precisely 1 degree higher than the bottom. That produces an oblique or a slant asymptote. Have you studied those?
Yes.
Okay. And the way you get the equation of that oblique asymptote is to do this division. Only you'd have to, in other words, let's say it's x cubed minus 2x squared. And now the rest of it does matter. Okay, and I'm dividing it by this. Okay, so you divide this by this using long division, and you will get a linear quotient. That linear quotient is the equation of the slant asymptote. And you might have a remainder. It doesn't matter. We don't care about the remainder. Do you know how to do this kind of long division?
Yeah, we haven't done it in a little while.
Okay. But you produce the quotient, typical quotients are going to be like x plus 5 with some remainder, okay? Well, it's this part that is the equation of the asymptote. Y equals x plus 5.
Okay, right.
So you only use that if the highest degree in the numerator is exactly 1 more than the highest degree in the denominator. And they'll never give you problems where it's 2 higher. In other words, you won't see x to the 4th over x squared.
Is that just because of pre-calc, or is that a...
No, I don't ever see it in calc either.
Okay.
I'm not sure what you get. I don't know whether you get... I think all slant asymptotes are straight lines, so I've never seen a curved asymptote.
Right.
What else did they want here? They wanted intercepts also?
Yes.
Okay. What's the y-intercept? What's x equal to when you're on the y-intercept? This is the key question, and most people don't know the answer, but it's actually pretty obvious. If I have a function, what's the x value right
Oh, 0.
there? Yeah. So the y-intercepts are the easiest things in the world to figure out. You just plug in x of 0, you get minus 4 in the numerator, minus 9 in the denominator. There's your y-intercept.
Okay.
Okay? X-intercepts are a little harder. What's y equal to when you're solving for the x-intercept?
0.
Right. Key thing to remember. X-intercepts, y is 0. Y-intercepts, x is 0. Well, that means I have to set f of x equal to 0 and solve that equation. So if I go back and set this whole thing equal to 0 and solve it. Solve that right there. Now, if I have a rational quotient equal 0, what has to be true of its numerator?
It's equal to 0.
Has to be. In other words, I can multiply both sides by this denominator, so I get x minus 2 times x plus 2 equals 0. Now, that's pretty easy to solve. X is either equal to 2, well, or minus 2. So whenever you see a rational quotient equal to 0, all you need to do is take its numerator and set it equal to 0 and solve.
Okay.
The y-intercept was 4/9, and the x-intercept is plus or minus 2. Did they want to know anything else?
No, just the graph now.
Oh, and they want you to graph it also?
Yes.
Okay. The way you graph these is you always start out drawing your asymptote grid. Well, I know I got vertical asymptotes at plus and minus 3. Here's the plus 3, here's the minus 3. And I got horizontal asymptotes at y equal 1. So there's my asymptote grid. And I've got a y-intercept at 4/9, which is about right there, if that line is 1. And I have x-intercepts at plus or minus 2. Now, whenever you see something like this, it's hyperbolic in nature. You know what a hyperbola looks like.
Right.
Let me scroll down and graph the most basic hyperbola. 1 over x. 1 over x looks like this. And it's got a horizontal asymptote there and a vertical asymptote there. Okay?
Does a hyperbola like that have foci?
Yes, it does, actually. There's a foci there and a foci there.
And it's the same Pythagorean theorem to find them?
No, well, no, actually, when you start talking about hyperbola that have been rotated by some angle other than 90 degrees, you're talking some hard math. Really hard math. In other words, who would have guessed that that's the equation of this hyperbola, right? Remember what our general formula for a hyperbola was? X minus h squared over a squared minus y minus k squared over b squared equals 1. Well, when you're dealing with horizontal or vertical major transverse axes, that is the formula. But if you rotate that major transverse axis by 45 degrees, it turns into this simple one right there.
Why is that?
Well,
What's the math behind the
the
equation?
math is really complicated. I'm not sure I could even explain it to you. Basically, what you do is you rotate the axis by 45 degrees. So instead of the picture looking like this, I would make my vertical axis look like that, my horizontal axis look like that. And now notice that relative to the red axis, that's a horizontal hyperbola.
Right.
But the adjustment involves trig functions. Why you haven't had it yet is because you haven't gotten to trig yet. And the handle, ellipses. In other words, you can also have ellipses that look like this. Ellipses don't come in just horizontal and vertical flavors. They come in all kinds of angle rotated. So if I said, what's the equation of that ellipse, that'd be really hard to figure out. You'd have to figure out what this angle was. Let's say that's a 45-degree angle. And then you'd have to go through some extremely complex math to figure out the equation of that ellipse. Same thing with hyperbolas. It just happens that if you rotate it exactly 45 degrees, it ends up being this nice, simple equation. Simpler than any equation of a horizontal or vertical hyperbola. Okay?
Oh.
Well, let's get back to the problem, because you're not going to have to deal with hyperbolas that are rotated.
Yeah, that's trippy.
It's very trippy. I had a kid come in one day. I met him at the library, and he was taking honors pre-calc. And this kid didn't know how to do algebra. And he comes in and he gives me these rotated conic sections and wants to go through the math on them. And I swear to God, he did not know how to multiply a linear term by a linear term. So anyway, let's go back to our problem. We've got our grid on there. And we don't have 4 quadrants, we actually have 6. We've got 1, 2, 3, 4, 5, 6. But we know our curve goes through that. Okay? Well, when I say that it's hyperbolic in nature, I mean it's going to look like this.
Right.
And over here, it's going to look like that. And then what does it do in the middle? Well,
Like a parabola?
yeah, it's going to look kind of like a parabola. It's not going to be a parabola, but it's going to look like that. And in fact, I'll bet this lower left one actually goes in the upper left. Bet this thing looks like this.
Okay.
And the reason is that usually when you go into an asymptote, you come from infinity and you come out the other side from the opposite infinity. In other words, I'm headed up to infinity there. I'm coming down from negative infinity on the other side of that vertical asymptote. Same thing here. I'm coming from negative infinity, therefore I'm going to come from positive infinity on the other side of it. That's not always the case, but it's usually the case.
Okay.
In other words, if I graph 1 over x squared, well, what does that look like? That looks like this. In other words, I go up to infinity and I come down from positive infinity on the other side. So there's an exception to that rule, but we're not done yet. That almost certainly is what this looks like. Usually the questionable part is the middle part. The middle part either looks like this or looks like this. You with me?
Right.
And
Yeah.
if it were the red line, then probably the rest of the thing would be that. Okay, in other words, that's one possibility also. The reason I knew this was not our curve, the red, is because I see 2x intercepts here. Well, there's no way that red line can go through 2x intercepts that are different. So I knew it was not the red. It was not, the middle didn't go all the way to the top. It turns around and comes back down to the bottom, which means this almost certainly is our curve. I know we're at 7 o'clock, but let me just graph this. It'll take me 2 seconds. Just make sure that we're looking at a correct curve here. X squared minus 4 divided by x squared minus 9. X squared minus 4 in parentheses.
Oh, you forgot the square piece.
I did, didn't I? No. Sorry. And divide that by x squared minus 9. Okay, I put it in right. Bingo.
Right.
Now, well, no. Yeah, that's almost exactly the way I drew it. Yeah.
Yeah.
The difference in these two curves, once again, is this is zoomed way in, this is zoomed out. And that's why in the upper curve you don't see the rest of the hyperbola. You only see the middle part. All right, William, you good to go for tonight?
Yes. Thank you very much.
And then we have one more tomorrow. And that's the last one before your final, right?
Yeah, I think so. I might or might not schedule one for Monday night. If I do schedule it, I'll probably schedule it this weekend.
That'd be easier. Here's my Monday schedule. So I got openings in Monday, but depending on when you could do it. In other words, I also have a couple hours scheduled on Monday. So the easiest time to schedule it, probably Saturday or Sunday.
Okay.
Either one. For me, it doesn't matter. Actually, Monday works better for me because Sunday I've already got 3 hours scheduled. And Monday I only have 2. So if you prefer Monday and you can fit it into my schedule, go ahead and do it for Monday. Your test is on Tuesday?
Yes.
All right. So Monday might work a little better for you.
Yeah.
Just from the idea that You want to do your tutoring session as close to your test as possible?
Right, keep it
Not
fresh.
sure I totally agree with that philosophy, but that's what all my students do, so I live with it. I actually think you might be better off scheduling it on Sunday. At least that would give you a chance to watch the recording on Monday, because you don't get the recording of your tutoring session until the next day.
Right.
So you might want to take that into consideration. I don't know. I don't know how useful those are to you, but if you didn't have anything else to study, that wouldn't be a bad thing to watch.
Okay.
Especially with tough material. Like tonight, we covered some really tough material tonight. You'd probably learn something by watching the video recording of tonight's session.
Okay.
But maybe, maybe not. I think it would be helpful, but only you really know. So I will talk to you tomorrow at 4:30.
Okay, great. Thank you very much, Mr. Callen.
Bye-bye.
Bye.